Okay, let's go ahead and get started. Just a couple administrative announcements to start out. First administrative announcement is that I only let you pick up your problem sets at the beginning of class if you promise that you won't then spend the entire class reading them instead of listening to me. Okay. Thank you. I guess now I'm doing administrative announcements, so who cares if you listen to me? Actually, I don't care if you listen to me. It's fine. I have no personal emotional investment in the issue. What was I going to say? Yes, no class on Friday. Okay, no class Friday. I actually went through my schedule for the rest of the semester, and we're actually on or even ahead of schedule, so I don't feel the need to schedule a makeup class at this time. I had suggested doing a makeup class the following Monday, but I forgot that I'm supposed to prosecute a thesis defense, so I won't be able to hold the makeup class at that time. So there are lots of Mondays left in the semester, so we'll see if we need to do a makeup class later on. So no makeup class, yes. Yeah, sorry, there was a question? Yeah, okay, good. Yeah, I said this, anyone who didn't get my email saying both of those things, let me know. Also, I'm giving you all an extension on the problem set until Friday at 5. I will be out of town, so make sure that when you turn in your problem set, you put it directly in the TA's mailbox so that he gets it. I am handing out, as usual, another problem set, which is sitting here somewhere, sitting here somewhere. I'll give you an extra week for it. I looked over my schedule for the class, and we have 1 week's leeway in terms of the problem sets. So this is it? Okay, so this is the week that you get off. Okay, next week is the week that you get off with no problem set. And after that, it'll be weekly problem sets for the rest of the semester until the take-home final. Any other administrative? Yes?
Do you know yet when the final...
Oh, yeah. We should decide that. The exam schedule is out. Okay, so here's my homework assignment for you is to figure out when your exams are. And then on Wednesday, next Wednesday, our next class, we'll have a discussion about when the take-home final will be. I think that the exams start the Thursday of the first week of December, and our last scheduled class is Friday, November 30th. Okay? So one possibility is we could have it over that weekend before the official exams start. So one possibility is that the take-home would be handed out November 30 and picked up on, which is a Friday, and picked up on Saturday, November 31st or December 1st, depending on whether 31 days half November. I don't remember. 30? Okay, December 1st. That's a possibility. Or we could do it Thursday to Friday. We could do it Thursday, November 29 to Friday, November 30. Or we could do it some other combination of days. We could also do it during the exam period. I think I'm technically not supposed to do that. Or maybe I am. I don't know. Or we could do it the following week, which is, because I don't think your exams start till that Wednesday or Thursday. So we could do it that Monday or Tuesday, but you probably have a lot of things to do that Monday and Tuesday. In the past, when I've done take-homes, weekends tend to be when people have more flexibility. And, basically what you should be looking for is that it's a 24-hour take-home exam. It's about the same length and difficulty as a problem set. Indeed, several of the problems that you have done on your problem sets are previous year's take-home exam problems. My intention is that it should take you about 8 hours. Okay. I write the exam so that it'll take you 8 hours. And you have 24 hours to do it. So that my intention is that everyone should get a good night's sleep. I'm also not very good at judging the amount of time that problems sometimes take. So so you should be prepared. It should be a 24-hour period when you can devote your time and energy to doing the exam. Okay. So those are a couple possibilities that I'll mention. Okay. I mean, does anyone know right now that those won't work? Like if I handed out something in class on Friday at 10 a.m. and it was due the following morning at 10 a.m. Is that? I guess that's true. Or I could hand it out on Saturday and it could be due on a Sunday. Then you have to come in on the weekend 2 days. And I know some people live far away, so Sunday to Monday, that's fine with me. Like, I have no life. I can come in anytime on the weekend. But, yeah, it's just a matter of what, I mean, Sunday to Monday, but then don't you have class Monday? I don't know. Yeah, Monday is the second to last day of class. Tuesday you have class also. But Tuesday is a Monday, right? Okay. Yeah, anyway, so is that better? Do you just want to say Sunday to Monday? Yeah, or we could say Thursday to Friday.
We could do like Friday at 5 p.m. to Saturday at 5 p.m.
Friday at 5 p.m. till Saturday at 5 p.m. Then you guys aren't going to get any sleep Friday night. We could do Friday at noon, right? Because then you'll be up all night working. Maybe you want that. Maybe we could do Friday at noon till Saturday at noon. But what do you have between 10 a.m. and noon? I know what you have. You have this class, right? So what if I could give you a 26-hour take-home final, and it could be Friday at 10 a.m. till Saturday at noon. Is that?
It's not like we could start during class, do we?
I could cancel class. I mean, I don't. Or I could hand it out. Or I could hand it out at the end of class. We could do something like. Do you guys have lots of classes Friday afternoons? Just one. Okay.
I have class till 6.
Class till 6. Yeah. Okay. Yeah. I mean, we could also do Saturday to Sunday. But then that means that everyone has to come in 2 weekend days. I could also hand out the exam by email. That's the other thing. So then you would only have to come in 1 weekend day. That's true. I can always email out the exam. So we could do Saturday to Sunday or even Sunday to Monday. Yeah. So that's a possibility. That way, if I hand it out on Sunday and you turn it in on Monday, then you don't have any. You don't have to come in on a weekend that you weren't planning at all. But it does mean you might be a little wrecked on Monday. But okay, that's fine. Maybe you're wrecked on Mondays anyway. Okay. What's that? Yeah, okay. Okay, so provisionally, we could also talk about Sunday, December 2nd to Monday, December 3rd. Okay, that's fine. That's fine with me. Okay. While we're doing this, any other questions of an administrative, non-physical nature? Okay, good. Physics. Okay. So, we began last week with a discussion of quantum statistical mechanics, where we decided that the correct way to describe an ensemble of systems is via a density operator typically denoted rho, which is the quantum operator that is the quantum version of the classical probability density on phase space of some ensemble of systems, which could reflect, for example, the fact that you have limited information about the exact state of the system, such as would be the case if you were describing a thermodynamic system where you know some of the macroscopic variables, such as pressure, volume, and so forth, that describe the system, but not necessarily all of the microscopic variables, such as all of the individual positions or momenta of the constituents of the system. And the rule for calculating expectation values of observables, such as an observable A that I have denoted here, is that they are computed by taking the trace of A times the corresponding density operator. And here, this expectation value denotes not just a quantum expectation value, but also an average over many, many quantum expectation values that are drawn in states which are drawn from this statistical ensemble defined by the density matrix rho. So, for example, if rho is an ensemble of states which says that you are in a state alpha I with probability pi, then rho, the operator, is just the sum of pi times the projection operator on the state alpha I. And if rho is just one projection operator, so that one of those pi's is equal to 1 and the rest are all 0, we say that rho is a pure state. And otherwise, we say that rho is mixed. And we ended class on last Wednesday by seeking a quantitative measurement of just how mixed a state is. So we saw an entropy functional S of rho, which quantifies how mixed a state is. So let's say the mixedness of a state. And the two properties that we demanded of this entropy functional were that S of rho should be equal to 0 if and only if rho is pure, and second, that S should be independent of the choice of basis in the Hilbert space. That is to say that S should not depend on anything but the eigenvalues of rho. Or if we wanted to say that a little bit more mathematically, if we did a unitary conjugation or a similarity transformation of the density operator rho, then that would leave the entropy S unchanged. And so that implied that S could be written as a trace of some function of rho. Simply because any function of the eigenvalues of rho can be written in terms of traces, either of rho, rho squared, rho cubed, and so forth. The third property that we have to spend a little bit more time discussing today is that if HA and HB are completely independent systems that are not coupled together in any way, described by density matrices rho A and rho B, that is to say, we have two systems, A and B, that are not coupled in any way, with density operators describing the ensemble of states in systems A and B, respectively, then the entropy of the collective system should be equal to the entropy of rho A plus the entropy of rho B. This is just the statement in the usual thermodynamic language that entropy is extensive. So for a non-interacting system, say an ideal gas, that would mean that the entropy is proportional to the volume of the system. In order to make this precise, we needed to introduce a little bit more language associated with entanglement. And in particular, we saw that if you have a state in the tensor product Hilbert space, so the combined system of HA and HB is described by the tensor product Hilbert space, HA tensor HB, which is the Hilbert space with dimension A times B, dimension HA times dimension HB. And the state is given by some density matrix rho AB, which is an operator on that Hilbert space. And the rule that we use for constructing the density matrices rho A and rho B is that rho A is the trace over B of rho AB, and likewise rho B is the trace over A of rho AB. Okay. So just to remind you of how that argument went, if we only wish to observe observables A which act on HA, then we trace over HB, and vice versa. So that means that, for example, the trace of over HA tensor HB of rho AB times A is equal to the trace over HA of rho A times A, where rho A is defined by tracing over Hilbert space B. I guess I should say HB. And just an aside, as an aside, this way of thinking about entanglement as leading to density matrices is a nice way of understanding, at least conceptually, the origin of the collapse of the wave function in quantum mechanics. Because the statement of the collapse of the wave function, as it is usually stated in your elementary quantum mechanics classes, can be regarded as the statement that upon measurement, a system evolves from a pure state into a mixed state. And we see, using this way of thinking about it, that mixedness can just be regarded as a consequence of the fact that we choose not to measure the exact quantum state of the apparatus performing the observation. And that if we were to keep track of its quantum state, then the system would evolve from a pure state to a pure state. So another way of saying that a little bit more schematically is that a density matrix is a measure of our ignorance of a system, and a measurement is a process by which the quantum system under consideration gets entangled with the state of your measuring apparatus. And if you then proceed to ignore the quantum state of your measuring apparatus, you have some ignorance about the exact quantum state of your system. And so you should then, if you're only performing measurements on Hilbert space A and not on your measuring apparatus, you can effectively consider that as an ensemble of states with some probability density. Okay. Are there any questions on that? So I went over that carefully but quickly last time. So are there any questions on that? I mean, I think that's a very important thing to think about. My goal today, however, is to use some of these considerations of tensor products, entanglement entropy, and so forth, in order to revisit this question of the entropy of a system and derive, or at least justify, a formula for the entropy of a system in terms of the density operator. Let me pause, however, and see if there are any questions. Okay. The notion of entanglement and tensor products and measurement and all that stuff is mathematically rather simple, but conceptually new, so it does take a little bit of time to wrap your head around. Okay, so in order to understand the consequences of this third postulate for the form of the entropy of a density matrix, so we have S is some trace of f of rho, or I could just define f of rho to be rho times g of rho. So I could call this trace of rho times g of rho, where f is rho times g. And then that is nothing more, nothing less than the expectation value of g evaluated in the ensemble of states associated with rho. So the entropy of a system is nothing more or nothing less than the expectation value of some Hermitian operator. And the question then is, what operator is it that will have the correct property so that S of the tensor product rho A times rho B is equal to S of rho A plus S of rho B? Well, that will become a little more clear if you think about this in terms of expectation values. In terms of expectation values, this is G of rho A times rho B. The expectation value being equal to G of rho A plus G of rho B. Okay. So we seek a function such that G of rho A times rho B is G of rho A plus G of rho B. Now, we can all think of a function, if we ignored the fact that rho was an operator and just thought of it as a function, then we can easily understand what that function would be. G of rho would have to be log rho, because log of rho A times rho B is log of rho A plus log of rho B. Okay. And because of the nature of the tensor product Hilbert space, rho A and rho B commute with one another, because one of them is rho A tensor 1, the other is 1 tensor rho B. So we can effectively regard these as numbers, ignoring the fact that they don't commute with one another necessarily, so that we can just go ahead and use our intuition about functions of numbers rather than functions of operators. So indeed, G will be equal to log rho, and S will be equal to trace of rho log rho. And in order to keep S positive, there's a conventional minus sign that goes out front. That's just convention. I often forget about it, so please remind me if I forget to write down that minus sign at some point in the future. Okay. So this is the form for the entropy that is additive for non-interacting systems. And this density, this has a name. It is referred to as the von Neumann entropy. Any questions? So have you guys seen this formula before? You may have seen it in a slightly different form. So you may have seen in classical physics we often refer in classical thermodynamics to the von Neumann entropy as the minus the sum over the states in the system of the probability of being in one state times the log of that probability. Now, as an exercise for you to make sure that you understand density matrices, I want you to prove to yourselves or convince yourselves that this is the same, that using the dictionary where rho was the sum over I of pi times the projection operator onto alpha I, that this quantum formula in the box is just the quantum version of this classical formula. And so this is then, for our purposes, the correct notion of the amount of disorder in a state, the amount of mixedness in a state, or the amount of lack of information that we have about the exact state of a system given a density matrix. Any questions before I continue? Now, this is not a class in information theory, either classical or quantum. I could spend an entire semester talking about quantum information theory and its relationship with quantum statistical mechanics. Instead, I'm only going to spend this class talking about the consequences of this form of the von Neumann entropy. Yeah, I think I will only spend this class discussing that. But it's a very interesting subject, and one I think that we, as a species, are only beginning to understand. The field of quantum information theory being one that is really only 20 years old, 25 years old. Okay. So the first question that I would then like to ask is, what is the relationship between this formula for the entropy and the thermodynamic notions of entropy that you have encountered previously in your classes on thermodynamics? So you guys have really never seen this classical formula for the von Neumann entropy? You really haven't seen that before. That's a crime. Okay. Well, you've seen it now, and you'll see it again. So in order to understand this, let me ask the following question. Let us imagine that we are in some sort of mixed state. We have some sort of ensemble of states. And we wish to ask what ensemble of states, that is to say, what density matrix, has the largest entropy given that we have fixed not the energy of the system, but the expectation value of the energy of the system. Okay. And this then is intuitively the notion of a thermal state. So to say that a slightly different way, we could say, what is the most likely state? That is to say, what is the state for which I have the most ignorance about the exact state of the system, subject to the fact that the amount of energy is fixed. Okay. And here energy is the expectation value of the energy upon repeated measurements drawn from this ensemble of states. So mathematically, what does this mean? This means that the entropy minus trace of rho log rho is maximized subject to two conditions. The first is that the expectation value of the energy is a constant. Okay. I'll give that constant a name. I'll call it E. It's a good name for the expectation value of the energy. And what is the other constraint? Well, of course, the density matrix must have unit trace because the sum of all probabilities should be equal to 1. Okay. So we're performing a maximization procedure where we maximize overall. We have a function s that depends on an operator rho, and we want to find the operator, that is to say, the ensemble of states, that maximizes the entropy subject to these two conditions. And we all know how to solve constrained maximization problems. Okay. Everybody together now? How do we solve constrained extremization problems? We use the method of Lagrange multipliers. I didn't hear all of you saying that with me. I'll just pretend that that's because it's early in the morning and you're all still half asleep. Okay, so how do we apply the method of Lagrange multipliers? I should emphasize, just as an aside, that we're used to minimizing or extremizing functions, that is to say, a function of a number rather than a function of an operator or a function of a matrix. But conceptually, there's no difference between extremizing a function and extremizing a functional, which depends on something more complicated like another function or a matrix. Indeed, you've already done that before in your life. You even used the symbol s to denote the functional that you are extremizing. When you use the Lagrangian formulation of mechanics to determine the classical path of a system given an action functional. You're doing the same sort of thing. Okay. And so the extremization procedure where we determine the density matrix is conceptually very similar to that sort of extremization problem. Okay. So how do we use the method of Lagrange multipliers? Well, instead of extremizing S itself, which is minus trace log rho log rho, let's let S prime be minus trace rho log rho plus two constraints that enforce these two conditions. So I'll introduce two Lagrange multipliers. I'll call them beta and gamma. And the method of Lagrange multipliers just says that we now extremize S prime, forgetting about the constraints, and we obtain an expression for rho that minimizes S prime in terms of beta and gamma, and then the Lagrange multipliers beta and gamma are determined by enforcing these two constraints. Okay. So how do we extremize S prime with respect to rho? Well, we want to take the derivative of S with respect to rho. Now, for an operator, that can get a little complicated. So the easiest way to think about that, taking the derivative, is we imagine varying rho in some way. So we take rho and we add to it some small variation delta rho, and then we expand S prime in a power series in delta rho and set the term linear in delta rho equal to 0. So what is the term linear in delta rho in the expansion of S prime? Well, we need to take, so first of all, from the first term, we have, so let me write it this way, we have the trace of rho log rho, which if you expand in a series order by order in delta rho, the term linear in delta rho will be the sum of two terms. You'll have delta rho times log rho coming from the variation of rho in rho log rho. And then you need to take log of rho plus delta rho and expand that in a power series in delta rho. And what will you get? You'll get, a minus sign because of that minus sign out front, times rho times the derivative of log rho, which is 1 over rho times delta rho. One comment I should make is that you might, in principle, be worried because I'm talking about operators instead of functions, that I should be being careful about the ordering of the various operators here. But because we're inside a trace, ordering doesn't matter. Rho times delta rho times 1 over rho is the same as rho times 1 over rho times delta rho, because you can always cyclically permute inside the trace. It's a fun exercise, and I encourage you to do it, to figure out exactly what the correct ordering prescription is if you weren't inside a trace. So that's an exercise that I leave to you, because in the present circumstance, now that we're inside the trace, it doesn't matter. Now we have to take into account the next two terms that come from the variation of the Lagrange multipliers with respect to rho. So the expectation value of h is the trace of h times rho. So that means that when you expand to linear order in delta rho, what you get is beta times the trace of h times delta rho. And likewise, the expectation value of 1 is just the trace of delta rho. So this will be plus gamma times delta rho. Any questions so far? And we need to set this equal to 0 because we wish this linear term to vanish for an arbitrary variation delta rho. So this should vanish for arbitrary delta rho. So what do we get? We get that log rho. Oh, I'm disappointed. Okay. Log rho is equal to beta h plus gamma. Okay. Let me make one small modification of my notation. Let me get rid of this minus sign up here. Or rather, let me redefine beta and gamma so that beta and gamma are minus what I wrote down above. You know, beta and gamma are Lagrange multipliers. I could just as easily use the Lagrange multiplier minus beta instead of beta. Let me choose this minus sign because that will make this notation that I'm using for the Lagrange multipliers completely consistent with the notation that you have already seen before, although you might not recognize it yet. Sorry, n minus 1. Or rho is e to the minus beta h times e to the minus gamma minus 1, where again, the Lagrange multipliers beta and gamma are fixed by the constraints that the trace of rho is equal to 1 and the trace of rho times h is equal to a constant e. Or if we want to write this in a language which is slightly more familiar to us, rho is e to the minus beta h divided by z of beta, where I've just identified gamma as the function of beta such that e to the minus gamma minus 1 is 1 over z times of beta, where z of beta is the partition function trace of e to the minus beta h. And beta, again, is fixed by the constraint that the expectation value of h is the trace of rho times h, which is z inverse the trace of h e to the minus beta h. So hopefully now the reason why I chose my signs in the Lagrange multiplier and the name beta in the Lagrange multiplier is clear. Beta is usually denoted temperature, or inverse temperature. And so we see that what we have derived here is nothing more or nothing less than the Boltzmann distribution, albeit written in the quantum mechanical form, where it is it is given by the canonical ensemble density operator e to the minus beta h. So we can see then that one way of deriving the Boltzmann distribution is demanding that we're looking for the density operator, the state, which maximizes our ignorance about the state, subject to the constraint that the expectation value of the energy is fixed. And often we don't know the expectation value of the energy. So instead of regarding this as a function of the expectation value of the energy, we could just regard it as a function of the corresponding Lagrange multiplier beta. Okay. And because beta is the Lagrange multiplier for the energy, we refer to beta, temperature, and energy as thermodynamically conjugate variables. In the same way that pressure and volume, charge and potential, or number and chemical potential are thermodynamically conjugate operators. There was a question.
Yeah, are you saying that your either gamma plus 1 is equal to your partition function?
Yes.
So, is that the counting might do, is that
Well, I mean, it's just the statement that rho has to be unit normalized, that the sum of all probabilities is 1. Okay. So does it have significance? Sure. Yeah. I mean, what can I say? The significance is that rho has to be such that the trace of rho is equal to 1. Okay. Have you guys seen this derivation of the Boltzmann distribution before? I guess if you haven't seen the von Neumann entropy, even in classical statistical mechanics, you wouldn't have seen this before. It makes clear exactly what temperature is. Temperature is the Lagrange multiplier associated with energy. And frequently, when we're studying a system, we don't have access to the expectation value of the energy. And so it's convenient to fix the temperature instead of the expectation value of the energy. But they contain exactly the same information. Questions? I mean, if you haven't seen this derivation, this means that you've gone through your entire lives being taught that the Boltzmann distribution is the right thing to describe a finite temperature ensemble, but you never knew why. Now you know why. Let me just introduce a little bit more notation, just so that you can make complete contact with some of the other notions that you have learned about in your thermodynamics classes. So sometimes we will use a special notation for rho. So we will write rho, which is 1 over z times e to the minus beta h, as e to the minus beta times h minus f. Where f is minus 1 over beta times log z is known as the free energy. And it is regarded as a function of the temperature, i.e. a function of beta. So why is this a convenient quantity to use? Well, in order to understand why this is a convenient quantity to use, let's calculate the von Neumann entropy in the canonical ensemble. So what is S? Remember, it's minus the expectation value of log rho. Or if I use my notation where rho is e to the minus beta h minus f, it's minus the expectation value of minus beta times h minus f. Or, using the fact, or beta times the expectation value of the Hamiltonian minus beta f. Okay. Remember, f is not an operator. F is a number, right? It's just some function of beta. It's the log of the partition function. Or beta f is minus s plus beta times h. Okay. So you may recognize this expression for the free energy in terms of the entropy, the temperature, and the energy. So if we refer to the expectation value of h as the energy of the system, then this may become a more familiar statement. Or if we multiply everything through by t, which is 1 over beta, that would be F is minus St plus energy. Okay. That hopefully is something that you have seen in your thermodynamics classes. But let's go ahead and stare at beta F for a second. So what is special about that combination of S and the expectation value of H? Well, we've actually seen that combination of S and the expectation value of H before. What is it? It's what I called S prime. So what was S prime? S prime was S plus beta times the expectation value of, or S minus beta times the expectation value of H. Okay. So that is what we called S prime, and that is the quantity that is minimized in the canonical ensemble. Remember that S was maximized, but S was maximized subject to the constraint that the expectation value of the energy was fixed, which meant that really S minus beta times the expectation value of H was maximized, or minus S plus beta times the expectation value of H was minimized. So another way of saying that rho maximizes the entropy subject to the constraint that the expectation value of the energy is fixed is another way of saying that rho is defined in the canonical ensemble to minimize the free energy. Systems at finite temperature seek to minimize their free energy. Not energy, as in standard classical dynamics, but free energy. So, if you have a thermodynamic system and you wish to understand what state the system will be in at fixed temperature, you compute the free energy as a function of your various dynamical variables, presumably some macroscopic variables that characterize the system, like pressure or volume, and then you find the state which minimizes the free energy. Questions? Yes?
So free energy is just this quantity that comes out from the back, right?
Sure.
But it doesn't mean anything.
Well, it means everything. It's the quantity that's minimized in the canonical ensemble.
So it comes out of the math. But if you look at a system, it doesn't.
What does it mean? Well, free energy is energy plus entropy or minus entropy times temperature. Yeah, it's a particularly funny-looking combination, but it is the right combination of, let's put it this way. In a system at zero temperature, that is to say in the microcanonical ensemble, a system would seek to minimize its energy. Okay, that's familiar. But you also know that systems seek to maximize their entropy. And so the minimization of the free energy, which is this particular linear combination of entropy and energy, tells you about the balance between those two opposing forces. The desire of a system to minimize its energy and the desire of a system to maximize its entropy. Okay. And so what is the role of temperature? Well, temperature is the quantity which sets the relative value of maximizing entropy versus minimizing energy in a system. So I think that's the physical understanding of this. And typically, the free energy is the most important quantity of interest in a system, a thermodynamic system. And it's the quantity from which all other of the various thermodynamic quantities we're interested in can be derived. Okay. So to see this, let's consider the following example. So let's imagine that we want to calculate the expectation value of the energy. So what is that? That's 1 over z times the trace of h e to the minus beta h. Or where z is, of course, the trace of e to the minus beta h, or e to the minus beta f. And so there's a clever trick that one can do to calculate the expectation value of h from z. We just notice that if you take the derivative of the partition function z with respect to beta, then that will bring down a factor of minus h. So that this expectation value of h can be written in terms of the beta derivative of z, or using the fact that, or another way of saying this is the beta derivative of log z, of course, and then using the fact that log z is minus beta f. This is the beta derivative of beta f, or f plus beta df by d beta. So that the entropy, which I remind you was beta times the expectation value of h minus beta f, is found just by plugging into this formula for the expectation value of h. And the beta f from here cancels the beta f from there, and s is minus, is it minus? It's just beta squared times df by d beta. So this shows you that the entropy can be derived from the free energy, provided you know the free energy as a function of temperature. Likewise, we sometimes define the specific heat C as the derivative of the energy with respect to temperature, or writing temperature as 1 over beta. This is minus beta squared times the derivative of the energy with respect to beta, which can likewise be expressed in terms of the second derivative of the free energy with respect to beta. So the specific heat will tell us how the energy changes as we change the temperature of the system, or vice versa, how if we change the expected value of the energy, the temperature will change. Any questions? So I should mention that because all of the various thermodynamic quantities of interest are expressed as derivatives of the free energy with respect to temperature, places or values of temperature for which a derivative, or let me say this slightly differently, values of beta for which f, or one of its derivatives, is discontinuous, means that some sort of thermodynamic quantities such as S, if f is discontinuous, or C, if the derivative of f is discontinuous, will diverge. And these special values of temperature, for which f or one of its derivatives is discontinuous, have a name. We call them phase transitions. So, if you have some complicated quantum system or classical system, and you compute its free energy as a function of temperature, and you find a place where the free energy or one of its derivatives is discontinuous, then we call that a phase transition. And the order of the derivative of f, which is discontinuous, is the order of the phase transition. So, very often when you hear people talking about phase transitions, you'll hear them say such and such is a first-order phase transition, a second-order phase transition, or so forth. And what they're talking about there is how discontinuous or how not smooth the free energy is as you cross this value of the temperature. So, for example, if f is continuous but its first derivative is discontinuous, then we would say that that's a first-order phase transition, and so on and so forth. And these different types of phase transitions are characterized by different sorts of thermodynamic quantities, such as the specific heat or some other thermodynamic quantity diverging. And which quantities diverge depends on what order phase transition you're considering. Very often, we can consider the system under consideration not just as a function of temperature, but as a function of other sorts of variables in the system. In solid-state physics, for example, you might dope a material by adding some level of impurity, and then you could study the free energy as a function of that amount of impurity, and you could discover a phase transition, such as a superconducting phase transition or something like that, as the amount of impurity is tuned across some value. And again, we would characterize that phase transition by talking about which order derivative of the free energy is discontinuous as you cross that phase transition. I'll spend a little bit more time. This is not a class on statistical mechanics, but I will, a couple more times in this course, talk by way of some examples about a few more issues in solid-state and condensed matter physics related to phase transitions. Questions? Have you guys seen this terminology before about the order of a phase transition? You have. Okay. So, what I would like to do now is just work out a few examples of the physics of a couple thermodynamic systems, their density matrices and their partition functions. And in particular, I'd like to introduce the two most famous types of thermodynamic systems, which would describe non-interacting particles. That is to say, free particles with either bosonic or fermionic statistics. And this will lead us to the notion of the Fermi-Dirac and Bose-Einstein distributions, respectively, both of which have interesting dynamics at low energy. One of the Fermi-Dirac distribution is characterized by Fermi surfaces at low energy, and the Bose-Einstein distribution is characterized by a Bose-Einstein condensate at low energy. So this may be something that you've seen before, but just as an example, I think I'll go through it at least briefly. Have you guys seen Fermi surfaces before? You have not. Sort of, or you have, maybe? Vaguely. Okay. And have you guys seen Bose-Einstein condensates before? Vaguely. Let's go through it again quickly, because it's interesting and it's worth seeing many times. And I think now, with our more refined understanding of quantum mechanics than you presumably had before, we can understand the dynamics of these systems a bit better. Okay. So what I would like to do is I would like to consider a system of some non-interacting particles, or some non-interacting states. So the energy of the system is going to be a sum of n nu times epsilon nu, where nu is an index which labels the different states in the system. Epsilon nu is the energy of the nth state, and n nu is the occupation number in a given state. So that for bosons, n nu can be 0, 1, 2, or indeed any integers, where for fermions, n nu must be 0 or 1. And the total number of particles is denoted by n, and that's the sum over nu, n nu. So the partition function of the system is the trace of e to the minus beta e, which is the sum over all allowed values of n nu, which characterize the different states in the system, of the exponential of minus beta e, and if we wish to introduce a chemical potential, plus beta mu times n in the grand canonical ensemble, where we don't fix the energy and the number of particles in the system, but instead we fix the temperature and chemical potential, mu, which allows the energy and the number of particles to fluctuate. Although, of course, the expectation value of the energy and the number of particles will be fixed. I could, of course, just consider the thermal ensemble, where the chemical potential is 0, but it's just as easy to consider the grand canonical ensemble, where the chemical potential is non-zero, and as we'll see, that actually leads to some interesting non-trivial effects. Okay. And indeed, if you want to consider, so as you will show on the next problem set, just as the canonical ensemble is the density matrix that maximizes the entropy subject to the statement that the expectation value of the energy is fixed, the grand canonical ensemble maximizes the entropy subject to the statement that the expectation value of the energy and the expectation value of the number operator are fixed. So what is the partition function? Well, we can use the fact that the energy and the number operator are just linear. You just add up the different particle states, where, again, the energy operator is the sum over nu times epsilon nu n nu, and n is the sum over nu times n nu. So I can write this as the product over nu times the sum over all of the allowed values of n nu, either 0 and 1 or 0 up to infinity, of this exponential factor. Now for a given particle state, so that's e to the minus beta epsilon nu plus beta mu all to the n nu power. all I've done here is I've rewritten this form for the partition function slightly, and I've factorized the exponential. So basically, I've written the sum over all of the allowed values of nu as a sum over all n1s, sum over all n2s, sum over all n3s, and so on and so forth. And then we can perform this sum. So for bosons, nu is 0 up to infinity. And so I can perform the sum, remembering that the sum over all n equals 0 up to infinity of x to the n is 1 over 1 minus x. So that for bosons, I obtain what's known as the Bose-Einstein distribution, which is the product over all states of 1 over 1 minus e to the minus beta epsilon nu plus beta mu. And likewise, for fermions, I obtain the Fermi-Dirac distribution, which is the product over all nu of 1 plus e to the minus beta epsilon nu plus beta mu. Just writing out explicitly the nu equals 0 and nu equals 1 terms. Presumably you guys have seen these before? Okay, good. So let's understand this in a little bit more detail. So let's consider the Fermi-Dirac distribution. So just as we could calculate the expectation value of the energy by taking the beta derivative of the partition function, we can calculate the expectation value of the number operator by taking the mu derivative of the partition function. And using the fact that z is e to the minus beta e plus beta mu times n, the expectation value of n is 1 over z times beta times the mu derivative of z. And using our formula for the Fermi-Dirac distribution, well, when you take the derivative, there's a z inverse which will cancel all of the, so you have to take the sum over all of the different terms in this product of exponentials written in the Fermi-Dirac distribution. So you'll get a sum over nu, okay, of e to the minus beta epsilon nu plus beta mu divided by 1 plus e to the minus beta epsilon nu plus beta mu. Okay. Here I've canceled the beta that comes from taking the derivative with respect to mu. And I'm using the fact that when you take the derivative of one of those terms in the product in the Fermi-Dirac distribution, you get a factor of 1 minus beta epsilon nu plus beta mu, and then you divide by z, so you get that guy in the denominator. And all of the terms that don't get hit by a given derivative just cancel, and so when you take the mu derivative, you end up just with a sum over mu of this guy that I've written here. So what is this? So let me rewrite this slightly. This is the sum over nu of 1 over e to the beta times epsilon nu minus mu plus 1. Okay. So this is the expectation value of the number operator, which is, of course, the sum over nu times the expectation value of n nu. So we see that the expectation value of nu, namely the probability that a given state is going to be filled or not filled in the Fermi-Dirac distribution, is 1 over beta times the energy minus mu plus 1. So it's illuminating to ask what this looks like as a function of energy. So if you graph the expectation value of n as a function of energy, you'll see that when epsilon is bigger than mu, the quantity in the exponential is going to be very big. And so the expectation value of n is going to be very small. Whereas when epsilon is less than mu, the exponential is going to be very small, and so nu is going to be very close to 1. Okay. So in particular, if you graph it, it'll look something like this. Sorry, that's not a very smooth function. Where in the 0 temperature limit, so as beta goes to infinity, i.e. the temperature goes to 0, the expectation value of n will go to 0 if epsilon is bigger than mu, and 1 if epsilon is less than mu. So it will approach a completely sharp distribution where n just drops off exactly when epsilon is equal to mu. And at finite temperature, where the temperature is, say, small but non-zero, so beta is big but not infinity, then you won't have this completely sharp distribution, but you'll have a slightly smeared out step function. Okay. So this gives us a nice way of thinking about the dynamics of a system of non-interacting fermions at low energy, or at low temperature, let's say. So at low temperature, states with energy less than the chemical potential are filled, and states with energy greater than the chemical potential are empty. So, if you wish to think about these states semi-classically, then you can think about constant energy surfaces as surfaces in phase space, and all of the states with energy less than mu are inside a particular surface known as the Fermi surface, given by epsilon equals mu in phase space. So that, for example, if you were to think about the phase space of the system, then you could draw the surface with epsilon equals to mu in phase space, which, for example, for a free particle would just be given by a sphere. Okay, so if the energy is equal to the sum of, is equal to p squared, say for non-interacting free fermions, then the Fermi surface would be E equals mu, namely that the length of the momentum vector is equal to mu, and the states that are filled would be those where the length of the momentum is less than mu. Okay. So the way that you think about a system of fermions at low temperature is that because of the Pauli exclusion principle, you can't have all of your states, all of the particles in one state. So instead they start filling up the states with low energy until they're all filled And the states which are filled are described by those states inside some Fermi surface, inside some surface in phase space. Or I suppose I should say in momentum space, really. At least for free particles, it's momentum space. And the nice thing about this picture is that even though I've derived it for a non-interacting system, this picture will persist, or I should say it often persists, for small interactions, or when interactions are turned on. And what will happen very often, although not universally, but often, is that the shape of the Fermi surface might change in some way. Okay, so it might look like that. It might be some complicated thing with some complicated topology, or it might be just some deformed sphere in some way. But nevertheless, even when interactions are turned on, you'll start filling up states one by one in inside this Fermi surface. And so if you want to understand the dynamics of the system, then the dynamics are given by, at low energy, which is to say low temperature, are given by fluctuations of the Fermi surface. So this is a universal way of thinking about the dynamics of all sorts of thermodynamic systems, which are described by systems of non-interacting or weakly interacting fermions. So even if you don't know exactly what the constituents of some system are, you can still think about a momentum space, and the states of the system is given by filling up some region in momentum space, and the dynamics are given by small fluctuations of this surface in momentum space. And this is known as the Landau theory of Fermi liquids. Okay. So in condensed matter physics, there's a whole theory that people have developed describing the fluctuations of this Fermi surface. And it's a very good model for all sorts of metals, for example, for all sorts of systems. Are there any questions on this? Okay. I only have 1 minute left, which is not enough time for me to derive Bose-Einstein condensation. It really won't take more than 10 minutes, say. But I don't want to try and rush it. So let me pause here and see if there are any questions. Yes?
When you go to your friction function for the funding, what is it, 1 plus?
It's a 1 plus an exponential, right? Right. So remember that fermions obey the Pauli exclusion principle, so that you can't have two particles in the same state. So that, because of that, nu had to be either 0 or 1. So I just had the first two terms in the sum. Okay. The nu equals 0 gives me that 1. The nu equals 1 gives me that guy right there. Good question. Any other questions? Have you guys seen Fermi surfaces before? Is that new? You have seen it. Where did you see it? Really? The 500 level one or your previous one?
300 level.
Okay, interesting. That's nice. Good. Who taught that class?
Prof. Psyche.
Okay, good. Any other questions? Okay, I'll see you guys not on Friday, but on Wednesday.